Okay, so this looks like a very hard problem. We have we have a vector field given to us, and we're supposed to compute flux where the surface is given with a spherical equation. Now, um, conveniently in that spherical equation, you solve for rho in the equation that's given with rho solved for. So you could take that and use the spherical graph parameterization and get a parameterization of the surface, and you could go chapter 5 style and compute that out. It would be brutally inconvenient, right? Um, the clever observation to make here is that rho is always positive. And so we used this trick in a previous problem somewhere. I think it was one of the exercises back in the section on these different coordinate equations. And since rho is always positive, what this means is whatever direction you happen to be looking, rho is positive. And so out there, the surface is at some point out that way. So whatever direction you pick, the surface is out that way somewhere. And in particular, altogether, this is going to be it might be lumpy, but this is some sort of a surface that wraps around the origin like this. Does that make sense? Okay. So this surface with this spherical equation is of that sort. Okay. All righty. So now let's compute flux. And let's see, we've got a surface f dot ds. We have options when we're computing flux. One thing I could try to do, it wouldn't seem likely that we would use Stokes' curl theorem here because we hadn't covered Stokes' curl theorem at that time, so that seems like an obvious not choice. We could use chapter 5 techniques. We've already agreed that would be brutal. So just in case, let's compute the divergence and see if we can instead compute this as a triple integral over the solid. Now, I don't know, the solid's going to be hard to describe. Maybe I could use spherical coordinates or something, right? But let's compute the divergence of the field. And maybe this will work out. So divergence of this vector field is, well, let's see here. Looking at the thing, we have the x partial of that. So I have 2x plus 2z minus 2y. Then let's see, the y partial there is 2y minus 2x. And then the z partial of the third term is minus 2z. And let's see here. Well, that cancels with that. And this cancels with that. That. And, of course, that cancels with that. Everything cancels, and the divergence is 0. So therefore, the integral is 0. So it was lucky break, right? It happened to be the case that we're doing a flux through a surface, which is a boundary, for one thing. We see there's a boundary of a solid inside of there. And furthermore, the divergence happens to be 0. So lucky break.
What if it's not a 0?
Then this would be a much harder problem. Much harder. Yeah, absolutely. And no, that's a very reasonable question. I didn't mean to be glib about that. Sorry about that. No, what I mean is that when I put together problems like this, I'm highly aware that I can't just write down a bunch of random stuff and hope that you can use some technique or another, and I hope it works out well for you, right? No, I very carefully construct examples where it will be reasonable by some means or another. Now, what means should you use? Well, that's up to you. And that's, one of the skills that I want you guys to develop is how to figure out, wait a minute, should I use chapter 5 techniques? Sometimes you should just use chapter 5 techniques. Sometimes that's the easiest way to do it. Sometimes that's the only way to do it. But sometimes Gauss's divergence theorem is useful. It's worth looking at. And so, for example, what we did here, very, very handy, right? On the other hand, maybe sometimes when you're computing flux, there are those occasions when Stokes' curl theorem is the right thing to do, right? But I won't put down a problem where of the several different options you have, they're all just brutally nasty, right? That wouldn't be decent of me, yeah. And it's not what I want to test, right? I want to test how well do you guys understand looking at a problem, considering the options. What we're going to talk about tomorrow actually is related to this. Called, I have a subsection called diagnosis. Namely, given a problem, how do you know what to do? What approach should I take? And there are hints that we're going to talk about. Yeah, so I want to make sure you guys know how to diagnose problems, how to then use the appropriate methods to solve the problem, and stuff like that.
Thank you.
Yeah, no problem. Yeah, okay.